Hello, Mr. Robinson's classes. This is Exponential Group Review Worksheet. I will make this the solution guide for basically the explanation behind everything. I think most things on the back will make sense, whatever. I think the graphs must be the most difficult part. I'll do my best in terms of explaining without over-teaching it per problem, but let me do the bit of lecture first, and then we'll take care of the rest after. All of our equations for graphing are coming in the form y equals a times b to the x minus h power and plus k on the outside. Now, when we took notes on this, we understood that every graph has some sort of scale factor, has some sort of shift and repositioning, and something else that basically makes this particular graph unique. In this case, there's a growth factor here as well, and it grows by certain amounts each time. What I want to do when I graph it, well, first of all, we can always graph with tables. So if you'd like to, there's no problem with just going ahead and graphing all these with tables, in which case you don't need to watch this portion of the video. What I'm going to do is make sense of these individual letters, A, H, and K. And obviously B comes in the form as well, but we use these three letters to help define where to start and how to work from there. Okay. A, like I said, it represents a scale or stretch factor. It also signifies your distance away from your asymptote when you're looking at what I call a starting value. And I call it a starting value because I can identify them helping use H and K as well. K is also the value of your asymptote. And your asymptote is the line of convergence, or basically the line that your curve does not cross through. It does not touch, it does not cross through. It will approach it in either the negative or positive x direction, but it does not actually ever hit it. And your H is your horizontal shift or displacement from the origin. So I'll talk about that because I'm going to say it in terms of x here as well. But anyway, I want to use these three values to signify where to start. After that, B kind of just comes into place. So let me talk about number one. Define A, H, and K. See what they are, and B as well. And see if we can come up with something through that. So number one, we have y equals 2 to the x plus 4. Now 2 is for b, which means the a value in front, which you can't see, is 1. There is no h that you can see, and k is 4. In terms of graphing this, what I want to do is a couple things. I want to find my asymptote, k equals 4. I want to graph that line. Let's go ahead and make it dotted. Whoops, that's not line. Let's make it dotted. So k, 1, 2, 3, 4. That's not green like I hoped. Hold on. Okay, this is the line which I will not cross from one direction. Okay, this is a positive, this is a value that is greater than 1 for b, which means my graph will either go this way, oh, that's what's dotted, or this way. Okay, you can either grow in the positive or negative direction. We are going to grow in the positive direction, not because b is positive, but because a is positive. When my stretch factor is positive, I'm going to be above my asymptote. You can try and plug in values to test this for yourself. Plug in 100 for x. 2 to the 100 power is a massive number. Plus 4 is an even bigger massive number, but it's a massive number. So when x goes this way, it's going very high up. When x becomes like negative 100, you'll go 1 over 2 to the 100 power, which is 1 over a very large number, which makes it a very small number. It's almost 0. It's like this number is 0. And when you add 4 to that number, you get almost 4, a number that's just above 4. So your graph will do something, we'll graph it in a second, but your graph will do something like from here, starting very close, I'll use another color, starting very close to the line, the asymptote, and eventually it's going to split away and do its thing. So we're going to be looking at a graph like that. So this is the behavior that we expect. Now let's go and locate that behavior exactly by pinpointing some points on here. First one I'm going to do that'll be most helpful to me in this kind of equation is I want to find out how A can help me, like where I can use this A number in my equation without having to use a table. The best way to do that is to make this whole value become 1. When this becomes 1, we get A times 1, which is A, and then plus K, your asymptote, means you're just going to be A units above or below your asymptote. So I'll give an example. Let's say I made this 1. In order to make this 1, I need to make this b to the 0 power, because b to the 0 power is 1. In order to make this b to the 0 power, I need to make x minus h become 0. In order to make x minus h become 0, I need to find the x value that corresponds with my h value. Okay? So this is the whole idea. I want to find the h value first in this case. So my h value here is 0, which means I want to go to x equals 0. When x equals 0, we'll get 2 to the 0 power, which is 1. That was our hope. 1 times 1 is 1. 1 plus 4 is 5. 1, 2, 3, 4, 5. So here's our first point. Now, I'm not thinking of this in terms of 5, though, because you look at this equation and you say, gee, where the heck do you see a 5? And you don't. I don't see a 5 anywhere. But what I do see is I have an asymptote of 4, and I have an a value of 1. And my a value, when my exponent is 0, my a value will appear as this far above my asymptote. So this 1 for a is signified right here, the distance between starting point and asymptote. Now, that distance is very important because once you found your starting point, everything else banks right off of that. Here's my b value. B says how many times, not how many times, B says what your growth factor will be. In other words, my distance between point and asymptote right now is 1. I'm about to take that distance and double it when I go over 1 right here. So 1 times 2 is 2. Now I'm going to double that distance. Here's my new point. Now I'm going to take this distance 2. And when I go over 1 more, I'm going to double that distance again. 2 times 2 is 4. This is probably up above here, right here. And if I did it again, I would double this distance. It would be 8. I'm going a little above at that point. I'm not going to keep going that way. But I can go backwards as well. Let's go to the left. Now, instead of doubling my distance, this distance would have been doubled to get 1. So in going backwards, I have to divide by 2. I have to halve my number if I doubled it before. So it goes there. 1/2 is my distance between. Here my distance is 1/4, and 1/8, and 1/16, and 1 over 32, 1 over 64, and you get a number that becomes very, very close to distance of 0 between your point that you're talking about and the asymptote. But it never becomes 0, which means your line never hits 4. It gets very close to 4, but never actually hits it. Now you can confirm this with a table as well. But there you are. The next one. A is -2. B is 3. H is 0. K is 1. I'm going to start with my asymptote. K equals 1. This helps me say where I'm going to be above or below at all times. B is 3, which means it's growth, which means I'm either going to grow positively or negatively. And I will grow negatively because A is negative. So this is the kind of graph that I'm going to be looking for. One that starts close to 1 and goes downward from there. So that's the expectation. Let's start with a starting point. Now, again, if you want to start with a starting point, you can always plug in 0 for x. I do caution you, though, if your shift is too far away from the origin, that you're going to get either a very small or very large number that's ungraphable. Plus, I want to give use of this value a, besides just the negative portion, so let's do that. In this case, x will be 0 again. Remember, I need to find the x value that's the same as h. My h is 0. 3 to the 0 power is 1. Negative 2 times 1 is negative 2. Negative 2 plus 1 is negative 1. So this first point is negative 1. Now, I'm only doing that calculation the first time to talk to you about it, but next time I do it, I'm just going to emphasize my first point is going to be this many away from my asymptote. Negative 2 away. A units away. I got my starting point. My next point will be 3 times the distance from my asymptote that my previous value was. This is negative 2 away. If I multiply this by 3, my next point will be negative 6 away. 1, 2, 3, 4, 5, 6. If I multiply it again, my next point would be negative 18 away. Now the point is not negative 18 in y. It's negative 18 away from the asymptote. So my point would be 2, I guess negative 17. Because negative 17 is negative 18 away from the asymptote of k equals 1. Let's go to the left. If I go over 1 this way, instead of multiplying by 3, I should be dividing by 3. So that's about 2/3. And then this is 2/9 somewhere over here, and it keeps going backward, or it keeps going closer to this value, but never quite hits it. So eventually, you got to start drawing that curve, which gets really steep. I mean, exponential functions go steep very quickly. So there's your graph. Final one, let's incorporate that horizontal shift so I can really talk about that x equals h mumbo jumbo and see why that a value is still important. A equals 3, b equals 2, h equals negative 1, k equals negative 2. Okay, start with my asymptote. Right there. Positive growth. Okay, positive growth. So I will be above, like that. Okay, now, my starting point. I want to select the value of negative 1 for x. Because when I do negative 1 plus 1, I get 0. The point is to make this value 1. And my distance is going to be 3 above my asymptote at x equals negative 1. 1, 2, 3. Don't take my word for that. Pause this video and confirm. Plug in negative 1 for x. See if you get 1 for y. But the important thing is not the number 1 for y. The important is 3 above the asymptote. I want to give use of my a value. My next number will be doubled the distance. Instead of 3 times 2 is 6 away. If I doubled that distance, I would be 12 away. A little too high. Let's halve the distance to the left. Divide this by 2, I get 1.5 away. Divide this by 2, I get 3/4 away. Divide this by 2, I get 3/8 away. 3/16 away, and so on. You'll get a curve like that. Again, please confirm these with tables. In fact, go to the site, graphsketch.com, graph all of these. But please confirm them with what I'm trying to accomplish for you. I want you to use, not that I want you to use, I want you to recognize that these values do have a purpose. And if you make sense of certain properties, such as b to the 0 power and everything else within that, then you can use these values and not have to look once at a table or have to do any computations of your own, except for when you double these numbers. Okay, this time I'm really going to speed it up. Now, I'm going to emphasize right now that that this entire ensemble right here, this should be in parentheses. Otherwise, we'd just be doing 1 to the x plus 3 power. It wouldn't be 2 to the x plus 3 power as well. This is your b value. It's a little ambiguous on the sheet. I would hope that more equations don't do that for you. A is 4, b is 1/2, h is negative 3, k is 0. My asymptote is at y equals 0. When I am negative 3, when I shift 3 to the left here, I will be 4 above the asymptote. Negative 3 and 4 up from the asymptote. Oh, by the way, this is your first sort of decay. Every time that you will have this value, we will decay from the positive direction. This is a plus 4. So we're going to look at a graph that goes this way. Well, a half arrow right there. So we're going to look at a graph that goes that way. Starting from here, when we go to the next number, we multiply it by 1/2 or divide it by 2. We get 2 away. Then we get 1 away from right here. And we get 1/2 away right here. And so on and so forth. How about over here? We'll be 8 away because we'll double our number going to the left. You can see right here, this is an example of why I wouldn't want to plug in 0 for x the first time, because you get 1/2. Not that it's very far, or not that it's a very small number, but sometimes you will get a very small number. I seem to remember us doing a problem in class where we started 7 away from the origin, 6 up from the origin, and your growth factor was 1/3. Your decay factor was 1/3. So your value was very minuscule. It was so small that you wouldn't want to plug in 0 to start. You want to get a starting point, a valid starting point such as that one. Okay, the next two problems, I need to pull out my calculator for it. We require a calculator. This is y equals e to the x minus 2, but I still will identify what my values are. A is 1, b is e. That is a constant. That's an actual value. H is 2, k is 0. Starting with my asymptote, k equals 0. When I am 2 away over here, I will start 1 above the asymptote. Now let's confirm that even with e. This would be y equals e to the 2 minus 2 power, which is y equals e to the 0 power. Now e is an actual value around 2.7. Etc., etc. But if I do any non-zero number, where is e on here? If I do any non-zero number to the 0 power, plugging it in, I get 1. So y equals 1 when x equals 2. So here's one of your points. The starting point did not change. The only difference that you have to do now is you have to multiply by e each time. So I'm going to, in my calculator, type e to the first power. Remember, when I go over to 3 here, I will be multiplying this by 1 amount of e, that far away from my asymptote. So I type that in and I get 2.718, etc. So I go over 1 from here. I'll go up 2.7-ish, about right there. Next one will be another multiple of e, so it'll be e squared. I type in e squared, that's 7.38. Whoops. So I go over 1 again. I'll go 1, 2, 3, 4, 5, 6, 7. Let's see, 1, 2, 3, 5, 6, 7.38 is about up there. This other way, it gets kind of weird. You'd have to do e to the negative first power. You'd divide by e, or 1 over e to the first. I'll get 0.36, and it gets kind of ridiculous from there. I'm going to stick with just those points and do that graph for you. By the way, this was growth because e is a value more than 1, and this was a positive 1 right here. Okay, final graphing problem. Y equals negative e to the x plus 3. A is 1. A is negative 1. B is e. I was going to say c. H is 0. K is 3. Start with my asymptote. K equals 3. This e represents growth. A is negative, so we will have negative growth in this fashion. Excuse me. My starting point is going to be 0. So at 0, I want to be 1 below my asymptote. At 0, I will be 1 away. Try and plug in 0 for x, and you'll see that you'll get 2 for y. My next value will be a multiple of e in the downward fashion. So this will be the same thing as last time. I think 2.7-ish away, then 7.3-ish away. 1, 2, 3, 4, 5, 6, 7.3. And then over on this side, it's about 0.3-ish away, and so on. Now E is a natural growth constant, one which we won't bury into too much, but it represents continuously compounded interest, word problems which we will get into on this, but I'd like to speed up. Find the exponential function that passes through the following points. Answer in y equals a to the bx form. What I'm going to do is use this equation. I'm going to set up a system using these 2 points. These are both x's and y's. I'm going to insert x's and y's into this equation right here. So I'll use the second equation first for the sake that I like the larger numbers on top if I can help it, because when I solve for a and b, I like to divide larger numbers by smaller numbers. So I'm going to plug in 160 for y and 5 for x, then 10 for y, and 1 for x. In a system of equations, you can do any manipulation as long as both sides of your equation are balanced. If I do division, if I divide 160 by 10, and I can divide ab to the fifth by ab to the first, because 10 equals ab to the first. Really, it's like saying you're dividing by 10 on both sides. The thing is, I don't want to divide this side by 10 per se. I want to divide it by terms that will help me out. So I divide both sides by some value, but it's the same value. I get 16. A divided by a is 1. B to the fifth divided by b to the first is b to the fourth. B to the fourth is 16, therefore b equals plus or minus 16. However, you have realized or recognized perhaps we have not looked at any negative b values. In fact, if you did that, which we will run into later this semester, you will get what is called, actually I don't know what it's called, but I'm going to look at it as oscillating divergence. Instead of your graph doing something like this or this, it would do something like this and keep going bigger and farther away. That is not exponential growth in the sense that we're looking for. You're not looking for the negative 16, even though that would not be in... Did I say plus or minus 16? I meant plus or minus 2. But you're not looking for the negative growth factor in that sense. You're just looking at the positive one. So b is positive 2. Once you have your b value, you may insert that value in for either equation to solve for a. When in doubt, go small. 10 equals a times 2 to the first power, which is 2. So a is 5. Your final equation is y equals 5 times, and I like the parentheses here, 2 to the x power. So you can try and plug in these values, and you'll see that they'll work, and you can actually graph this, and you'll see all that. This was using elimination method. I'll go and use substitution method for this other one so we get some practice in one form and in the other. Let's start by creating an equation. I'll go ahead and plug in this one right here. We'll get 8 equals a times b squared. Now, you'll notice if I do this equation as well, we'll get 32 equals a times b cubed. You'll notice that both of these things have a in them. So I can, and it's very easy to solve for a in either one. I just have to divide by b squared or b cubed. So if I go and take a look at this equation and I transform it and solve for a, I can use 8 over b squared, and I can substitute that in for this a value right here. So now I'll get 32 equals 8 over b squared times b cubed. Now I have b cubed over b squared, that is just b. So this is gone. That's gone, and now you have 32 equals 8b, and b equals 4. Now that you have b equals 4, I can go ahead and reinsert this back into my equation for a. Now that I have something to solve for a, I don't have to plug it into one of these equations. So I can take it, insert it right into there, and I'll get a equals 8 over 4 squared. A is 8 over 16, so a is 1/2. So my final equation then is y equals 1/2 times 4 to the x power. Okay, and there was that one right there. Your final equation, or your final set of points for we'll find an equation. Kind of sucks, got some fractions here. I personally don't like to deal with fractions as long as I can look at it without fractions, even if your answer has fractions in it. So I'm going to start by writing these equations. 25 over 3 equals a times b squared. Now I'm going to transform this guy. I'm going to multiply both sides by 3. This will get rid of that 3 on bottom, and it'll move a 3 over here. I'll get 25 equals 3a b squared. It's no matter to me, but if you were without a calculator and you had to do division later, because I'm going to do elimination on this one, then maybe it's good to do. Maybe it's good to have it like this. Same with this one. You got 1/15 equals -1. Oops. 1/15 equals a times b to the negative first power. Okay, so I multiply both sides by 15, I'll get 1 equals 15 a times b to the negative first power. Now, I could put this as all over b to the positive first power, but I'm about to do some division here, and I don't want any fractions if I'm going to already deal with division. That'd be a fraction within a fraction. So you divide everything. 25 divided by 1, I get 25. Okay, now we get a fraction. 3 over 15 is 1 over 5, so I'm going to get this thing all over 5. A over a is 1. They cancel. B squared over b to the negative first. That's b to the 2 minus negative first power, which is b cubed. So here I have b cubed on top. All right, so there's my setup. Keep going. B cubed equals 125 if I multiply both sides by 5. And b equals positive 5. Okay, so we got some squared away right there. I'm running out of room. I'm going to move all over here. Okay, let's choose an equation here. I'll use one without the negative b to the first thing right here. Let's go over here. 25 equals 3a 5 squared. 5 squared. 5 squared is 25 times 25. And you can see if I divide both sides by 25, I'll get 1 over here. So I'm going to get 3a equals 1. So a equals 1/3. Final equation, y equals 1/3 times 5 to the x power. Not too bad. Good to go. You know what's funny about these equations is they give us fractions here for a. We've never graphed with fractions for a. I'm really surprised they give us something of this magnitude instead of fractions for b. Anyway, I digress. Would the following exponential functions model growth or decay? In other words, would they be increasing or decreasing? These words they can be ambiguous. Increasing refers to going further in the direction that you're going. That means this or this. These are increasing. This is said to be negative growth. Think about this as driving. And this is a hard example if you have not done physics or calculus because you have not done word problems that involve position versus velocity versus acceleration. But pretend like you're in a car and this is the front of the car and this is the back of the car. Excuse me. So pretend like the front of the car is driving forward. So up is driving forward, down is driving backward. If you are increasing speed, you can be increasing speed in this direction, going in drive, or you could be increasing in this direction, going in reverse. I can go 30 miles an hour backwards, and that's faster than 10 miles an hour backwards, in other words. And I can increase my speed as I keep going. So although I am going in a negative direction, so to speak, I am not decreasing. I am increasing in that direction. So that's what's important. In other words, what we're trying to find is if b is greater than 1 or if b is less than 1. If b is equal to 1, then it's not exponential, it's linear. So we're not looking for a scenario like that. Okay, first one. So it doesn't matter what this is. This can be positive or negative, so we can talk about positive or negative increasing stuff, but it's still growing. So ignore that. We're just looking at the e. E is greater than 1. It's 2.7 something. So this is growth. B in this case is 1/3. Now it's a little ambiguous again. To me, this looks like 1 to the x power divided by 3. So you could actually write this equation as y equals 2/3 times 1 to the x minus 1. And this would be linear. But I don't think this thing intended to be that way. I think they really meant this to say your b value is 1/3. And if your b value is 1/3, 1/3 is less than 1. This is decay. Let's see what these look like actually. This one would look like, on the left, this would look like it's going like that. This decay would start from the top and would go down. It would look like it's going like that. And it would arrive at an asymptote. And this one right here, doesn't matter what this thing is, it's positive value. This is greater than 1. So this is growth. Because this is positive over here, this would go up this way as well. There you are. Okay, I got 6 more problems, and I gotta actually rush through these a little bit. I got class this morning. You invest $2,300 into a bank that compounds continuously. Underline that whenever you see that. And yields 3% annual interest. How much money will you have in the account in 7 years? And here's the hint. Now, E is used for continuously compounded interest. So, or this function. Now, this is no different than your y equals ab to the x, or ab to the cx if you consider c to be a scalar multiple for your exponent. This is still that function where a becomes y, meaning your final amount after x years. P is a, meaning your initial amount at 0 years. B is E, is your growth rate, 2.7-ish. X is your time, t, and r is a constant value, which you will insert based on the problem that represents some sort of scalar multiple. Now, the thing about continuously compounded interest is that your interest gets interest, and that's what that 3% is. Your 3% tacks on more and more as time goes on, which is pretty awesome. So you invest $2,300, so your P, your initial value, is $2,300. Compounds continuously, that's your E. 3% annual interest. So R is that annual interest. 3% is 0.03. How much money will you have in 7 years? So after 7 years, what happens? Basically, what it's wondering is what is your interest after 7 years? So let's do that first. I'm going to do R times T, which is 0.03, times 7, which is 0.21. Your interest after 7 years has risen to 0.21. It yields 3% annual interest, so every year you get 3% more interest than you previously had. Not 3%, 3% more. So your exponential function, if you just want to write it as y equals ab to the x, you're solving for a. This is 2,300 times e to the 0.21 power. That's all you're plugging in. Your answer, I have to go to my calculator for this, 2,300 times e to the 0.21 is $2,837. Well, here, the number is 2837.459538. And you're like, okay, well, is that your answer? That's your calculation, but what do you need? How much money? So this unit is in dollars, and for this to be in dollars, you also might want cents. For cents, we go only to the hundredths place, and we will round. Well, you know what? Will we round up? It's actually a good question. I would actually round down, and I'm going to give an example why, because you don't yet have 46 cents in your account. So I do apologize if I said to anybody in group thing, oh, you round up or whatever else. But round to the nearest, to the bottomest hundredth in your case. 45 cents, not 46. Probably on the next day, you probably have 46. I don't know. Your grandmother set up a bank account for you as a, why is there a comma there? As a very generous present 12 years ago. T is 12. The bank compounded continuously at 4.2% annual interest. So it did at that amount. So 12 years later, it's going to be a different amount. Let's go and figure that out now. R times T is 12 times 4.2. Was that for? I think it's 50.4. Let me try that. 12 times 50.4. So now you have interest 50.4%. Screw that up. 4.2 is not. It is 50.4%, but it's not 4.2. It's 0.042. So that would be 0.504, which is 50.4%. There you go. I didn't want to raise it to such an extreme power. You just check the balance, and there is this amount in the account. So this was 12 years later. That was not your initial investment. That's the investment you have now. 28252. How much did she originally invest? We got to solve for P. So we'll get 28252 equals P times E to the 0.504 power. That is a 4. e to the 0.504. The reason why I'm doing this first, besides letting you understand what the problem is doing, is order of operations becomes really important here. And you might screw something up if you multiply by t well after the fact and not use parentheses, and you have a calculator that doesn't show what power you're at, all that stuff. So I want you to be very careful with that. The other thing I want you to be careful with is rounding before your final answer. So that's why I'm going to first start by writing this as p equals 28252 over e to the 0.504, because I want to do this all in one step to avoid any sort of rounding before my final answer. So 28252 divided by, now in parentheses, perhaps, I need e to the 0.504 power, and I will get syntax error. I had the close parentheses up in the above. There we go. I will get 17067. Excuse me. 17067.29828. How much did she originally invest? In this case, you might want to round up, because if you have this much money, you don't want to say you had only 29 cents in there. Otherwise, you probably wouldn't reach the amount that you have. Round up to 30 in this case. I'm not too peculiar about whether you round up or down. In some senses, it really depends on the problem, but round to the nearest hundredth for money. For the next problems, I think you have fish coming up. You have fish. Round to the nearest whole fish. Fish in a pond are increasing at an annual rate of 18%. The initial population was 343 fish. How many fish will there be in 3 years? Okay. This is going to be a y equals a times b to the x problem. In the sense they're not continuous. It's not continuously compounded interest. They're increasing at an annual rate of 18%. It means you have 18% more than you previously had. So you don't want your, so this refers to your growth. Right? This is growth, so this is b. You don't want your b to just be 18%. You want to be 18% more than what you had before. If you have 18%, you can, so what you can do is take 18% of 100% of what you had and then add to that. A better way to do that is just take 118% of what you had. So, B is 1.18. The initial population, A, was 343. 3 years, X. Let's find out what Y is going to become. Y equals 343 times 1.18 cubed. Got to do 1.18 cubed first. This basically says you do 18% more the first year, 18% more the second year of your new number, and 18% more the third year of your new number. Okay, so I get 1.64 something. Multiply that by 343, and I now have 563.559, etc., something like that. Fish. Round to the lower fish in this case. How many do you have? You can't say you have 564 fish yet, because you don't. You currently have 563. 564th is on its way, but it's not there 3 years later. Fish in a neighboring pond have caught a terrible fish disease. It is killing them. That sucks. If the fish are decreasing or dying at an annual rate of 23%, and there are 800 fish right now, how many will there be in 30 months? So it looks like the 23% means 23% less fish than the previous year. So if you have 20% less, they're not saying 23% of what you had. Like if you had 100, now you have 23. They're saying if you had 100, now you have 77. You have 23% less then. So for B, we're going to do 100% of that minus 23% of that, which, as I said before, is 77%. So we're going to take 77% of what we previously had. There are 800 fish right now, and 30 months. Now, will I write x equals 30? Whoops. X equals 30? No, because this is an annual rate. We need to figure out what this converts to in years. In order to do that, divide by 12. That's 2 and 6 twelfths, that's 2.5. So that's 2.5 years. So after 2.5 years, what do you got? So here we go. We got y equals 800 times 0.77 to the 2.5th power. Gotta rush this a little more. Times 800. I have 416.214, something like that, fish. Now, fish are dying. So the question for this, it's either 416 or 417. This one's more your philosophy. If you have 416 point whatever, did the 417th fish already die, or is the 417th fish dying? That's up to you, but you need to round to the nearest fish in one case or the other when they are dying. You'll notice the difference, though. You did not get the 564th fish yet in this case. Okay, last two. Half-life problem. Carbon C14 has a half-life of 5730 years. Okay, half-life. Let's first identify the equation here. In this case, for half-life, B will be your decay rate of 1/2. And this x over t, don't let it confuse you too much. I'll go back to the previous problem if it helps. Notice, we did a fraction here because we had to do a certain unit conversion. X over t is nothing more than your number of half-lives. So I'll do that first. When I do this, t represents the half-life of the element, or the isotope. X represents the number of years you have undergone. So x over t is how many half-lives there have undergone. So, carbon C14 has a half-life of 5,730 years. How much C14 would be left for a 22 milligram sample after 2,001 years? A is your initial value of 22 milligrams. X represents the number of years that have passed already. Now, half-life represents the how long it takes for a substance or an element to have halved what it previously had. So, in other words, we started off with 22 milligrams of this stuff. After 5,730 years, there will be half that amount, which is 11. So if I plugged in 5,730 for x, you would have gotten the value of 11. All that told. So let's talk about that ratio again, the x over t thing, before I continue with this. X over t is 2001 over 5,730. It has not yet endured a half-life. In fact, it's not even halfway there to enduring that half-life. 2001 divided by 5730 is some wacky number, 0.349, etc. I want to keep the number that's in my calculator, not round it. But this number says how many half-lives it has undergone. It has not even undergone one half-life yet. So we know our number should be greater than 11 for sure. So your exponential function is y equals 22 times 1/2 to the x over t power, which is that 0.349 number. I'm not plugging in 0.349. I'm using the number that I had. I'm going to raise it to that value in my calculator. You can't see this. I'm going to multiply this by 22, and I'll get 17.27. About. It didn't say what to round it to, but this is pretty good. 17.27 milligrams. So this is how much is left. Okay. I want you to, once again, keep in mind, if x became 5730, I'd have 5730 over 5730, which is 1. I would be raising this to the first power. 1/2 to the first power is 1/2, and 1/2 of 22 is 11. So when x becomes some multiple of t, that'll say how many half-lives it's undergone. If I had an x value that was twice the amount of t, it would have undergone 2 half-lives, which would mean I would have divided this by half. Well, not by half. I would have divided this in half to get 11. And I would have divided that number in half to get 5.5, etc. So 2 half-lives would have left you with 5.5 milligrams of C14. Final problem, now I gotta go. Bunny population at Tulum Meadows doubles every 2 years. Doubles, this is the growth. That's your B value. Every 2 years, alright, this will have something to do with our time here. This is another kind of ratio thing we need to talk about. If there are currently 89 bunnies at Tulum Meadows, how many will there be in 200 years? Okay. Remember, x isn't necessarily just one number, because, we don't talk about that. There are currently 89 bunnies, so we're going to start with 89. We need to see how many there will be in 200 years. Now, x isn't just 200. Remember, it doubles every 2 years. So in order for it to double every 2 years, you need to see what happens every 2 years, which means, here, let's see, what's a better example of that? Okay, here's what I want to say. If it doubles every 2 years, that means after 200 years, it has only doubled 100 times. It has not doubled 200 times. So this is the same idea as half-life. This is the same idea as this other thing with this rate and such. You need to know what your x value is. You can be dividing by something, you can be multiplying by something, but you need to say, how many times am I doubling this in the end? I'm only doubling it, so yeah, that's where this 2 is coming in right there. I'm doubling every 100 years. And b is 2, so let's go ahead. Y equals 89 times 2 to the 100 power. Now we get to see what 2 to the 100 power is. Finally, yay. 2 to the 100. That's a big number. And then times 89. So, my number is so big. Are you serious? That is, geez, that's a lot. Y equals, so here's what my calculator says, and I'm going to cut off some of the decimals here. 1282, I'll do that. And then it says times 10 to the 32nd power. I mean, do you realize how big that number is? To humor you, I'll type it. This is 1, and then count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 5, 6, 7, 8, 9, 30, 31, 32. I know I cut off some bunny amounts here. In fact, I should have put in those other ones. This is how many bunnies. I don't know why I'm laughing. This is how many bunnies there would be. I like bunnies. I think that's why it's funny. Google something called like an island full of bunnies or something like that, and like they're super adorable. Like there's an exotic island or something like that that's full of nothing but like bunnies. Like people visit. There'll be that many bunnies. Okay, so there are some limitations to some of these things. Poor Tulum Meadows. All right, that's all I got for you. Thanks for watching, and good luck with everything.